So if you want to fly from New York to Tokyo, um, two cities that are sitting roughly on the same horizontal band of the northern hemisphere.
Right, they're practically across from each other.
Exactly. So the absolute fastest way to get there is actually to point your plane north and just fly straight up toward the Arctic Circle.
Which sounds completely wrong.
Right. It sounds completely absurd. But today's deep dive is really all about the hidden mathematics that makes that absurdity an actual reality.
Yeah, and we are looking at a highly specific piece of source material to unpack this today. It's a self-contained HTML and JavaScript code snippet.
Yeah, a literal code file.
Exactly.
Yeah.
And the developer basically built this fully functional tool. They call it a Great Circle Vertex and Waypoint Calculator.
Wow, okay.
And it contains all these raw trigonometric equations. Plus, we also have this visual snapshot, like an image of the graphical interface actually in action.
Right. And our mission today is really to take this raw code and demystify the geometry that governs, well, global travel and mapping. Because, I mean, when you look at a flat wall map, your brain just immediately draws a straight line between two cities.
You can't help it. It's how we're wired.
Right. You just assume the straight line is the shortest distance. But the flat map is basically lying to you.
It is. The code we're reviewing completely proves that straight lines on flat maps are spatial illusions. I mean, that massive curve up to the Arctic on a flight path, that's the literal definition of spatial efficiency on a globe.
It's so wild to think about.
Yeah, and this document, this code, it essentially bridges the gap between the curved physical reality of our planet and the flat digital screens that we use to navigate it every day.
Okay, let's unpack this.
Yeah.
Because right at the top of this JavaScript file, the developer establishes the foundational physics for the universe that this calculator operates in.
Right, they have to set the rules.
Yeah, so it defines the Earth itself. It sets a variable r for radius at exactly 6,371 kilometers.
So the developer is explicitly committing to a spherical Earth model for all this math.
But the Earth isn't a perfect sphere, right?
Well, no, I mean, our planet actually bulges around the equator because of its rotation, so it makes it an oblate spheroid.
Right, oblate spheroid.
But for the purpose of these navigational calculations, treating the Earth as a perfect sphere with that 6,371 kilometer radius, it actually provides this incredibly accurate baseline.
So it's close enough for the math to work.
Exactly. It simplifies the equations without really sacrificing the real-world precision you'd require to, actually plot a flight path.
And that perfect sphere model is the entire reason we're forced to deal with what the code calls great circles.
Yes, the great circles.
So for anyone trying to visualize this, just imagine holding an apple and a knife.
Okay, an apple.
Yeah, and if you slice the apple perfectly in half, going straight through the absolute center of the core, the circular line that cut makes on the skin of the apple is a great circle.
That's a really good way to picture it. And the equator is obviously the most universally recognized great circle.
Right, because it goes right around the middle.
But you can tilt your imaginary knife at any angle you want, like diagonally across the Atlantic or vertically over the poles.
So as long as the slice passes dead center through the Earth's core, it counts.
Exactly. The geometric rule here is that the shortest distance between any 2 points on the surface of a sphere, it will always lie along the edge of one of those specific core intersecting slices.
But knowing that the path is this giant hoop, I mean, that creates an immediate logistical issue for navigation, doesn't it?
Oh, absolutely.
Because when you take that three-dimensional tilted hoop and you smash it down onto a two-dimensional flight map, it looks like a massive arch.
Right, and an arch has to have a peak.
Exactly. And the developer's code tackles this exact problem first.
Because if we're plotting a route over the curve of the Earth, there literally has to be a singular moment where the plane hits its absolute highest or lowest latitude before coming back down.
So the code calculates this peak, which it calls the vertex.
Yes. The source material defines the vertex as the point of maximum or minimum latitude reached by the minor great circle arc.
Okay, minor great circle arc. But the code makes a really careful distinction here between the types of vertices that a pilot might actually encounter.
Right. It separates an interior vertex from what it labels an endpoint vertex.
And when I was reading this, I was picturing a baseball game.
Oh, okay. Go on.
So if I throw a long, high pass from the outfield all the way to home plate, the ball travels in a sweeping arch.
Right, a huge parabolic curve.
Yeah, so the interior vertex is that exact singular moment the ball is highest in the air before gravity pulls it back down to the catcher.
And the global flight path operates under that exact same logic.
It's the highest point.
Yeah. With an interior vertex, you basically take off from city A, and your latitude steadily increases as you climb toward the poles, right?
Mm.
And you hit that mathematical pick, the vertex, and then your latitude starts to decrease as you fly down to city B. So the peak happens somewhere over the ocean, or maybe a landmass just halfway between the two cities.
But the code also labels some scenarios as Endpoint A or Endpoint B with, quote, no interior vertex.
Right.
So sticking to the baseball analogy, that would be like a line drive straight down.
Exactly.
Like if I just drop a baseball from a balcony directly to you standing on the sidewalk below, there's no cresting arch in the middle of that journey.
No, of course not.
The absolute highest point of that trip was literally the second the ball left my hand.
What's fascinating here is how the developer actually finds that peak mathematically. Because, I mean, think about it. In a purely digital 3D space, a computer doesn't have eyes to just look at a curved line and spot the top.
Right, it can't just see the arc.
No, it has to calculate the tilt of the circle using vector mathematics. Specifically, it uses a vector cross product.
Okay, I'm going to try to visualize this because vector math gets incredibly dense.
It really does, yeah.
So if we have our starting city and our destination city, the computer treats those two locations as 3D arrows, originating at the Earth's molten core, just piercing right out through the crust.
Exactly. You've got two arrows pointing out.
So the cross-product math takes those two arrows and generates a third arrow, sticking out at a perfect 90-degree angle to both of them.
You've captured the geometry perfectly. That third perpendicular arrow, it acts as an axle.
An axle.
Yeah, it dictates the exact tilt and spatial orientation of that imaginary knife we were talking about slicing through the Earth.
Oh, wow.
But once the computer establishes that plane, it still needs to find the actual peak on the physical surface of the planet.
Right, so it projects the poles. The code takes the coordinate of the North Pole or the South Pole and mathematically drops a line straight down onto our tilted flight plane. So it basically finds the single spot on our great circle that gets as physically close to the pole as the tilt will allow.
Exactly. The computer just finds where the pole casts its shadow on our route, and that shadow is our vertex.
Okay, so we've mathematically anchored the absolute peak of the route.
We found the top.
But unless you're parachuting out of the plane at the exact top of the world, just knowing the peak doesn't really help an autopilot navigate the entire journey.
No, it doesn't do much on its own.
Right. We need a way to plot the slope of the curve leading up to that peak and then coming down from it.
And that requires a major shift in the code because we have to move away from vector math and enter the realm of spherical trigonometry.
Spherical trigonometry.
Yeah, leaning heavily on this framework known as Napier's rules.
Which is wild, by the way. John Napier was this mathematician working in the 16th and 17th centuries.
Long before computers.
Yeah. I mean, sailors and explorers were using these exact same principles to navigate wooden ships across oceans hundreds of years before anyone was declaring variables in JavaScript.
Well, the physical reality of the Earth hasn't changed, right? Navigators have always had to deal with the Earth bulging outward.
It's just a constant problem.
Yeah, think about a flat piece of paper. If you draw a triangle on it, the three inside angles will always add up to exactly 180 degrees.
Right, that's basic geometry.
But now, take a marker and draw a triangle on a basketball.
Okay.
Because the surface of the basketball bulges, the lines of the triangle curve outward.
Oh, right. They're not straight lines anymore.
Exactly. And if you try to measure the angles inside that curved triangle, they add up to more than 180 degrees.
Wow.
So standard flat plane trigonometry just completely collapses. It doesn't work.
And Napier codified the rules for solving the lengths and angles of these bulging spherical triangles.
Yes, and the calculator uses the vertex we just pinpointed as a master reference anchor.
Okay.
From that peak, it calculates any other location on the route. And the code calls those locations waypoints.
Right. And in the source code, navigating this bulging triangle brings us to this highly specific variable for distance.
Yeah, the distance angle.
It's denoted by the Greek letter sigma, which kind of looks like a tiny O with a horizontal tail on top.
Sigma.
And the code explicitly calls sigma the distance angle. But wait, I really have to push back here.
Okay, go for it.
Why are we using angles for distance? Like, shouldn't the distance along a flight path to a waypoint just be measured in standard kilometers or miles?
Yeah, that expectation is totally a byproduct of living on flat surfaces.
Really?
Yeah. On a sphere, distance is fundamentally an angular measurement from the core.
Okay, walk me through that.
Imagine standing on a giant globe. Draw a line straight down from your feet to the exact center of the Earth.
Okay, I have my line.
Then draw another line from the center of the Earth straight up to your destination.
So like a V shape starting from the core.
Exactly. The angle between those two intersecting lines at the core, that is your distance.
Okay, so if I travel from the equator straight up to the North Pole, I've covered a quarter of the globe, which means those two lines meeting at the core are exactly 90 degrees apart.
Yes,
So the distance traveled is literally 90 degrees.
you got it. And the code utilizes sigma to represent that exact angular distance away from our peak, the vertex.
But a pilot still needs to know how many actual miles or kilometers they have left to fly.
Right, and because we established earlier that the Earth's radius is 6,371 kilometers, the developer just includes this brilliantly simple mathematical conversion.
So it turns the angle back into a normal distance.
Exactly. The calculator takes that distance angle, sigma, it converts it into radians, and then simply multiplies it by the 6,371 kilometer radius.
And that's it.
That's it. The output is the actual physical distance in kilometers. It's a really seamless translation from pure spherical geometry into a tangible, real-world metric.
That is so elegant. Let's look at how the code uses that sigma angle to find the specific latitude of our waypoint, though. Because the formula in the material states, let's see, the sine of the waypoint's latitude is equal to the sine of the vertex latitude multiplied by the cosine of sigma.
Right, that's the equation.
But instead of just reading the equation aloud, help me picture what the computer's actually doing geometrically.
Sure. Imagine creating a right-angled spherical triangle on the globe.
Okay, on the bulging basketball globe.
Yes. The three corners of this triangle are the equator, our known vertex, and our unknown waypoint.
Got it.
We know how high up the vertex is, and we know how far away we have traveled from it along the curve, which is our sigma.
Right, our distance angle.
So multiplying by the cosine of that distance essentially scales the height of our vertex. As you move further away from the peak, the cosine shrinks the value, which lowers the resulting latitude perfectly in sync with the physical curvature of the Earth dropping away.
Oh, wow. So as you slide away from the top, the math just pulls your latitude down with the curve.
Exactly.
But that only explains the up and down position. A waypoint obviously requires two coordinates.
Right. You need longitude, too.
We need the left to right. And when we look at the longitude formula in the source material, it's really not just straightforward addition.
No, it's quite complex.
It's asking for a delta, like a difference. And to get it, the code uses an arctangent function called ATAN2. It divides the sine of our distance by the cosine of the vertex latitude multiplied by the cosine of the distance. Just trying to visualize that division gives me a headache.
It is a lot of math crammed into one line of code.
What is that mechanism actually doing under the hood?
Well, finding longitude on a sphere is notoriously tricky because the vertical lines of longitude, they're not parallel.
Right, they all pinch together at the north and south poles.
Exactly. They converge at the poles and they spread out the widest at the equator.
So you can't just say, add 50 miles to move east.
No, because 50 miles east, near the pole, crosses way more longitude lines than 50 miles east at the equator.
Right, okay.
So the ATAN2 arctangent function is basically this specialized tool for finding an angle on a grid.
Okay.
It calculates the precise heading or direction on that curved surface by comparing two things.
Which are the...
How much we are moving forward along the path versus how much we are moving sideways across those converging longitude lines.
Oh, okay. So it calculates the angular difference between the peak and our current spot.
Exactly.
And once the computer finds that difference, it simply adds it to the original longitude of the vertex. The vertex really is the master key to this entire map.
It dictates everything.
You find that single shadow cast by the North Pole using the cross product, and then every single other dot on the Trans-Pacific flight path is just a mathematical shift away from it.
The entire journey is relative to that one point.
But, seeing these dense formulas written in a text file is one thing. The developer actually built a fully interactive visual interface to let users just play with this geometry.
Yeah, which is so helpful for actually grasping what this math does.
Right. And they embedded 4 built-in preset journeys to test the tool.
And the presets chosen by the developer are highly intentional. They included Seoul to Paris, Seoul to London, Seoul to Vancouver, and New York to Tokyo.
Which are all massive trans-hemispheric flights.
Yeah.
They perfectly showcase the counterintuitive nature of great circles, because their routes push incredibly far north, completely shattering our flat map expectations.
If you look at them on a normal map, they just look like these huge, useless detours.
Exactly. And to let a user test this curvature, There is a control bar positioned right in the middle of the interface. It's labeled Waypoint Calculation from Vertex, and it features a sliding scale for our distance angle, sigma.
And this slider makes the abstract spherical trigonometry completely tactile for the user, like you can actually feel the math.
Which I love.
It allows you to adjust sigma from a negative 180 degrees to a positive 180 degrees.
So you basically just grab the slider on the screen and physically drag it, and as you move it, the JavaScript dynamically plots your exact waypoint anywhere along the entire 360-degree global circumference of that route.
In real time.
And we actually have a visual snapshot from the source material showing this exact mechanism frozen in action.
The color coding in that snapshot does a phenomenal job of translating the dense math into an intuitive visual language.
It really does.
We see a map of the northern hemisphere focused heavily on the upper, colder latitudes.
Right, and here's where it gets really interesting. Cutting across the top of the globe, just sweeping right over the landmass of northern Russia, is this thick green line.
That's our flight path.
Yeah, that green line is the calculated Great Circle route, the actual geometric reality of the shortest distance. And sitting directly at the absolute crest of that green arch is a red marker.
And that red marker is the visual proof of the vector cross product that we discussed earlier.
The axial shadow.
Exactly. The computer calculated the 3D plane, it projected the North Pole, and it planted that marker right at the vertex.
And the interface panel reveals the exact coordinates for this specific interior vertex.
Yeah.
It's located incredibly far north.
Extremely far north.
It's sitting at 64.21791 degrees north latitude and 58.7838 degrees east longitude.
So it's stationed way up near the Arctic Circle.
Right. But as you trace your eye further down the green line to the right, descending from the peak, there's a second marker, a blue one.
And the blue marker represents the dynamically calculated waypoint. It is the visual embodiment of John Napier's spherical triangles just working in real time.
The snapshot shows us exactly how the user's slider controls that blue dot, too. The slider for the distance angle, sigma, is locked in at 11.2 degrees.
So mathematically speaking, that means the blue marker is sitting exactly 11.2 degrees of angular distance away from the red vertex.
And the calculator automatically runs that conversion metric we talked about earlier.
With the radius.
Right. It takes the 11.2 degrees, multiplies it by the Earth's 6,371-kilometer radius, and tells us right on the screen that our blue waypoint is precisely 1,245.4 kilometers away from the vertex.
And the output data printed in the image completely confirms the geometry is working flawlessly.
How so?
Well, the red vertex was sitting at roughly 64 degrees north. We moved 1,245 kilometers away from it along the curve, and the calculator places our new blue waypoint at 62.04374 degrees north and 83.2651 degrees east.
So the latitude is decreasing.
Exactly. The blue dot is physically lower on the screen than the red dot, perfectly demonstrating the downward slope away from the interior vertex.
Wow. So every single calculation, the cross products, the ATA and two functions, the scaling cosines, it all just culminates in placing that blue dot in the exact right physical location on a curved planet.
It's just brilliant engineering.
It really is.
Yeah.
So what does this all mean? I mean, we've spent this deep dive exploring variables, cross products, and centuries-old trigonometry.
It's a lot to take in.
But for me, dissecting this calculator fundamentally alters how I experience digital maps.
I agree.
I mean, the next time you are sitting on a long-haul flight to Tokyo or Paris, and you're watching that tiny pixelated plane icon crawl along a massive looping curve on the seatback screen, you aren't just looking at a simple graphic anymore.
No, you're watching Napier's rules and great circle vertices executing continuously.
Right there on the screen.
Yeah. This single piece of HTML and JavaScript beautifully exposes the friction between the three-dimensional reality of our planet and the two-dimensional tools we have to rely on to navigate it.
It's crazy.
It serves as this stark reminder that the most direct path in physical reality rarely looks like a straight line on our digital screens.
You really just have to trust the math of the sphere, not the paper.
Absolutely. And if we connect this technical deep dive to a broader human perspective, it leaves us with a really compelling question.
Oh, I like where this is going.
Well, think about it. If our standard flat maps distort physical distance so drastically that finding the shortest path requires complex spherical trigonometry just to draw it correctly.
Yeah.
How else do these flat representations distort our worldview?
Oh, that is a fascinating angle
Yeah.
because we are incredibly conditioned by the rectangular maps hanging on our walls.
Right. We look at a flat projection and implicitly assume certain nations or cultures are entirely isolated from one another because they are printed on opposite edges of the paper.
Like they're worlds apart.
Exactly. But it begs the question, what other cultural, political, or social relationships seem incredibly distant on our flawed maps, but are actually sitting right next door to each other on a sphere?